All right. So we were seeing the unilateral Laplace transform, which was requiring the initial conditions for solving differential equations. And we have seen that the initial conditions for higher order derivatives would correspond to the list that I have indicated in the previous time. Like for the first derivative, we need the initial condition in time. And for the second derivative, we need the initial condition in time, that is x of 0, as well as x prime of 0, which is the initial condition of the first derivative. And for the third derivative, we need the second derivative, the first derivative, and the signal itself in terms of their values at t is equal to 0. And it goes on like this. So you may remember these from differential equations. So this last example that I will show you will be just for you to remember, maybe, which is this kind of a constant coefficient linear differential equation, which is what we have. Again, from differential equations, you may remember that this kind of a thing, a differential equation, has two parts in solving. One part which could be solved in a combined way, but we usually don't prefer to use that. So I will also split the question into two parts, which was the particular solution and the homogeneous part. So these two parts correspond to essentially, let's say, part 1 and part 2. Part 1 corresponds to 0 initial conditions, but there is an input. So let's solve it that way first. And these two parts will not touch to one another. And when you combine those two parts of the solution, it gives you the complete solution. So with 0 initial conditions and the input, so we have 0 initial conditions. Plus the input first we have HU Laplace transform of the system. I can immediately the Laplace transform of the as square here 3 and coming from here in the denominator to you need to my voice is glitchy, says one of you. It may be due to several things. It may be from my connection side or from your connection side. As long as it is not completely cut, we will have to continue, unfortunately. But I'm just telling you this. So I will be writing again. And therefore, the voice is hopefully not so much important. The H of S, the unilateral Laplace transform, or the normal Laplace transform of H of T is this. 1 over S squared plus 3S plus 2, okay? And the input, XU of XU of S is unknown yet, but it has to be known. So we have to put the X of T here. What is X of T, in other words? What is the perturbation that is applied? X of T is alpha times U of T. So we apply a unit step. with an amount of alpha. That is just the input, and for the particular solution we need to know that input. So xu of s is therefore the Laplace transform of xu of t, which is alpha over s. Which makes the output yu of s to be equal to hu of s times xu of s, which is equal to alpha over s times s squared plus 3s plus 2, which can be, the denominator can further be split to the multiplication parts, the first order systems, in other words, as 1 over s times s plus 1 and s plus 2. Okay. Now, a critical step afterwards is the splitting of this into first order systems in the additional, in the multi, which you can the realization using building blocks, but we want to invert this into time domain. We want to find y of t for the particular solution. What is y of t? That's what we are looking for. And for that, you have to do it like a over s plus b over s plus 1 plus c over s plus 2 or something like this, okay? You've split into first order systems, and you find a and b and c. You determine these from the 3 equations, and you will see that a is equal to alpha over 2, b is equal to minus alpha, and c is equal to, again, alpha over 2. That will be your observation when you solve for this, for which the overall output will be in the Laplace domain like this. Excuse me, it's not alpha squared, it's alpha over 2 over s plus 2. From where you find the output y of t to be equal to, in an alpha parenthesis, everything is scaled by alpha, 1 over 2 minus e to the minus t plus 1 over 2 e to the minus 2t times u of t. This is the particular solution with 0 initial conditions. With 0 initial conditions. This is the result. But this result is not the only result. There is in other words, without any input, just according to the initial condition, it will run. So part 2 is no input with initial conditions. So the output at 0 must be something. Let's give a value of beta. We have been using alpha before, so now let's use beta. And the derivative initial condition is gamma. Okay, these 3 Greek letters. One, alpha is used for the input, beta and gamma are used as the initial conditions. So with these initial conditions, I can write the differential equation and convert it into the Laplace domain like this. There is an s square yu of s coming from the second derivative, but there is a minus beta times s and minus gamma. which are the time initial condition, which was beta times S, and there's also a derivative initial condition coming as gamma. So this essentially comes from d squared by dt squared y of t, okay, plus three s times y s 3 beta, and this comes from d by dt, or 3 d by dt y of t, okay, that compound will produce this part, and plus 2 yu of s, which comes from 2y of s. And the right-hand side that we will solve is now nothing. Or let's say it does not reflect to the solution. So I will leave it as x of s, x u of s. Let's keep it like this. And when we do it like this, so this comes out to be an inaccurate way of making a representation. Let me say it like from this output, I will not be interested in the output region. I will split it into the two parts later. So in fact, we need to know the input at this point, but now I'm incorporating the initial conditions too. But when I show you the output, you will see which parts really corresponds to the input part and which part does not really correspond to the input, but it runs as a self-input and self-oscillatory part of the output. Now, from here, we need to solve for y of s, yu of s, and that will be equal to. Now, things are getting a little bit complicated here because we have to put everything into yu of s parentheses, and it will give me, again, a third order expression in the denominator, and there will be also something in the numerator coming from coefficients such as beta and gamma and this beta, etc. So in between, I have to write something like a few minutes later. We come up with this result because it's not the systematic that we're looking for, it's the result that I want to show you. This is one coefficient that comes out. This is another coefficient that comes out. Right. So this result actually includes everything. It contains both the homogeneous part and the particular solution that we have. That's indicated. This is the particular solution, and it's the same result that we have obtained above this one. Okay, so that is the alpha part is the part that we know, and it comes from the perturbation, the unit step. As you see, there is also this 1 over S or alpha over S appearing here, which is the input essentially. And this is the system response. But meanwhile, the system response, the same denominator of S plus 1 times S plus 2 here and here also appears from the intrinsic initial conditions of beta and gamma as well. So these two terms, actually there are more than two terms, but two clusters of terms coming from the initial conditions are also appearing here, which could be considered as the homogeneous part. All right. So how are we going to split this into first order systems? Well, it's not very easy. We have done it for this, for a generic alpha value, but we need to also know the values of beta and gamma too. So there must be some numerical values for that. If they are left as parameters as beta and gamma, like this, then solving this and splitting those things will be difficult. It was also very difficult for this one, but now we need to do it again for this and for this, which is a bad idea. In such questions, we usually come up with numerical values. Excuse me, not that one. Yeah. Numerical values like alpha is something. It's, let's say, 2. Beta is equal to 3. I don't know what's happening to this pencil. And gamma is equal to minus 5. Minus 5. Something like this maybe. Then it will be easier for you to handle these terms them into components. And most of the components will be shared then, because the denominator parts are sharing a lot of similar components, like S plus 1, S plus 2 is here, S plus 1, S plus 2 is here again. And there's also S plus 1, S plus 2 here. So several things will be merged, and eventually it will be a third order system. Like this, a third order, meaning that not the system, but together with the input, it will be third order output, meaning that we will have 3 components of exponentials, and those 3 components of exponentials with these numerical values, if you do, can be obtained as 1, which is e to the 0t, minus e to the minus t, plus 3 e to the minus 2t times u of t. When you solve or when you find the inverse Laplace transform of c. This is the approach that we may adopt. And I'm showing you so that you remember the fact that this Laplace parameter S was actually used is actually something that you must remember from differential equations. And now you see that things are strongly related with each other. So S is related to omega, which is the frequency, the Fourier transform. And omega is related to the frequency response. Therefore, it is related to the impulse response. And these system responses, signal representations, frequencies, multiplication in frequency and convolutions in time, etc. They are all related to one another, which you have partially started seeing in circuit theory in your previous courses, because in circuit theory there was also an omega. There were phasors, if you may remember. So you started already seeing the Fourier transform in the form of a phasor, but you didn't know that what you were really seeing was actually the Fourier transform, and a different name was used for phasor. For example, do you remember the phasor representation for the capacitor? What was the reactance of a capacitor? In other words, it was 1 over j omega c. And for an inductor, it was j omega L, which is indicating that as the frequency increases, the effective resistance of a capacitor decreases, because if the frequency increases, it's in the denominator, and the denominator part increases, so the resistance of that capacitor decreases. And that's something that we know. And conversely, if the frequency increases, the inductor starts showing more resistance, because omega is in the numerator and j omega L increases. That's how a normal RLC circuit behaves. And for R, there is no frequency dependence. And whenever there is a frequency dependence, as you see, there's a J factor coming into the picture, which is meaning that we have a two-axis overall resistance, a real part and an imaginary part, and there is a magnitude of it, etc. Those are the topics that you have been seeing in circuit theory. So everything must support one another mathematically in electrical engineering and in many of the engineering studies as well. We have these components of circuits, which is at the heart of an electrical engineering. And there is differential equations, there is circuit theory, and there is signals and systems, from which you may proceed to telecommunication-wise, thinking about how to analyze systems, telecommunication systems. You will also learn how to analyze control systems, which are the two fundamental parts of electrical engineering again, except the digital controls. And even in that digital control systems, we will proceed from here with the discrete time analysis, because there's also the discrete time Fourier transform, which will continue to become a discrete time Laplace transform in a sense, but the name will not be the Laplace transform anymore. It will have a different name, and we will talk about it after the break. So right now I want to stop because this example has finished, and I have also talked a little bit about how everything is related to one another. Students usually tend to ask this question, are we going to use it? Why are we learning this, etc.? Yes, if you may be doing electrical engineering, then of course you are going to use it, because everything depends on one another. Without the knowledge of the other, you may not continue your education. And in the fourth year, this is the third year, your junior year. The next year is your senior. And in the next year, all the things that you will see, most of the things, will require these fundamentals. So try to learn them as good as possible. Now, I want to stop, and I will give a 20 minutes break. So let's meet at 9:50. 10 minutes before 10 o'clock. All right. Now, do you have any questions? I can give you a few seconds, but I didn't encounter any questions from the chat. So if you have no more questions, I'm stopping now, and we will meet at 9:50.